In the previous videos, we've been really focused in on the intricacies of the snowpack. Now I want to shift our focus to a little bit more big picture thinking. So in this video, we're going to talk about mountain weather. And we're going to talk specifically about the ways that mountain weather builds different kinds of snow climates. Now, a major driver of mountain weather is a process called orographic lift. So we're going to dive into that right here. So here we've got a mountain, and unless we've got some sort of funky inversion going on, generally the lower elevations of the mountain are going to be warmer than the upper elevations. Now, while the wind is capable of coming from any direction, geographical zones will have a predominant wind direction where the wind tends to come from. So in this case, the wind tends to flow from left to right. Now, storms will follow that predominant wind direction. So in this case, with the prevailing winds moving from left to right, storms will also tend to move from left to right, and as they get pushed upwards on the mountain from the warmer elevations down low towards the cooler elevations up high, the rate of condensation within the cloud is going to begin to increase. And ultimately what this does is it causes the cloud to begin to precipitate, which in the winter takes the form of snow. And as a result, on the windward side of the mountain, you're going to end up with quite a thick snowpack. As the cloud gets pushed up and over the mountain by the prevailing winds, it will begin to drop from those cool upper elevations into warmer elevations. And as the cloud warms, its rate of internal condensation will decrease, which translates to a decreased rate of precipitation. So the leeward side of this mountain is going to be much drier, and as a result, it has a much thinner snowpack. We often refer to the leeward side of a large geographical feature, such as a mountain range, as the rain shadow. So now that we have this concept of orographic lift, I want to apply it to some familiar geography and try to puzzle through how it might contribute to the formation of different snow climates. So here we've got the west coast of North America, Alaska stretching down into British Columbia, then Washington, Oregon, and the northern portion of California. And a rather impressive geographical feature of the western portion of North America is the Rocky Mountains. So these start up in Alaska with the Alaska Range, and they continue all the way through British Columbia into Washington, Oregon, and California. Now, because of the jet stream, the prevailing winds on the west coast of North America tend to travel from west to east, which means that moisture-rich clouds produced in the Pacific Ocean are going to be pushed interior up and over the Rocky Mountains. And because of orographic lift, these clouds will tend to drop the majority of their precipitation on the windward or coastal side of the mountains. So ultimately, as a response to these trends, you end up with some really broad climate regimes. So on the coastal side, you end up with a zone that gets more precipitation. And interior, you have a zone that gets less precipitation, which we could call the rain shadow of the Rockies. And between these two extremes, you have a zone that gets an intermediate amount of precipitation. Because the ocean has such a moderating effect on ambient air temperature, you also end up with some broad trends in terms of air temperature. So that coastal zone that gets more precipitation also tends to see warmer winter air temperatures relative to the interior zone, which tends to be a little cooler in the winter. Now, as we've learned before, ambient air temperature and the depth of the snowpack can have some real impacts on the grains that make up the snowpack. And as a result, these three distinct weather climates also produce three distinct snow climates. So on the coast, where it tends to be a little warmer with deeper snowpacks, you end up with what's called a maritime snowpack. And interior, where it tends to be a little cooler with less snow, you end up with a continental snowpack, and that zone between the two is referred to as the intermountain snowpack. So now that we have established the existence of these three different snow climates, I want to spend a little time talking about each one. So we're going to start with a maritime snow climate. Maritime snow climates are coastally influenced, which means that they occur in mountains that are adjacent to the ocean, which translates to two major impacts, which we've already established. For one, the ocean provides a tremendous amount of water vapor, which translates to more clouds and more precipitation. And second, the water in the ocean has a very moderating effect on ambient air temperature, so air temperature in these zones tends to be relatively warm in the winter. Examples of maritime snow climates in south central Alaska include Girdwood most winters and Turnagain Pass. So let's zoom in and apply some of what we've learned about snow metamorphism to a maritime snow climate. So at the base of the snowpack, we've got the Earth, and as we established before, in a maritime snow climate, there is a lot of precipitation, which translates to a thick snowpack. Technically speaking, we generally say greater than 3 meters is considered maritime snowpack. Now, thinking back to the earlier metamorphism videos, a thick snowpack and a warm ambient air temperature is going to contribute to the formation of rounds, which means that maritime snowpacks tend to be fairly stable. This also means that when a maritime snowpack becomes unstable, it's often the result of a direct weather event. So a good example of this is mid-season rain, which is extremely destabilizing until it freezes. A truly maritime snowpack is also going to show a good capacity for healing, so persistent weak layers like buried surface hoar, or in this case, facets, are going to begin to round and heal as a result of that thick snowpack and warm ambient air temperature. Now that we've talked about maritime snow climates, let's take a minute to talk about continental snow climates, which occur inland and have no coastal influence. So these mountains, because they exist far from the ocean, don't have that moderating effect of the water. And as a result, the ambient air temperature around these mountains tends to be relatively cold. Furthermore, because there's not this huge source of water vapor and clouds are dropping precipitation before they even get inland, these areas tend to receive less precip overall. Some examples of local continental snowpacks includes Hatcher Pass some years and the interior portion of Alaska. So let's go ahead and apply what we already know about metamorphism to this particular setup. So here we have the Earth, and with very little precip, you end up with a thin snowpack. Now, technically, a continental snowpack is less than 1.5 meters deep. Now, as we learned before, a thin snowpack in conjunction with cold ambient air temperatures results in faceting. And because these facets occur in a climate regime that consists of a thin snowpack and cold ambient air temperatures, they're going to tend to create weak layers within the snowpack that resist healing over time. This means that continental snowpacks will often harbor weak layers for weeks or even months after active weather has occurred. The third kind of snow climate I'm going to talk about today sits somewhere between a maritime and a continental snowpack. And that is an intermountain snowpack, which is a snowpack that has some coastal influence. And because of this limited amount of coastal influence, intermountain snow climates tend to see a moderate amount of precip. So the snowpack depth tends to be sort of in between. It's technically anywhere from 1.5 meters to 3 meters deep. In addition, the ambient air temperature tends to be sort of moderate, so warmer than a continental but cooler than a maritime climate. Because intermountain snow climates occupy this sort of in-between space, they tend to see a wide range of instabilities. So like maritime snowpacks, they will see instabilities that are directly driven by heavy precip or wintertime rain. But like a continental snowpack, they often harbor weak layers deep in the snowpack for weeks or months on end. A good example of a local intermountain snow climate is the Summit Lake area past Turnagain Pass. Hatcher Pass can also behave fairly intermountain in some seasons. The fact that you can classify Hatcher Pass as an intermountain snow climate one year and a continental snow climate another year leads me to the last point I want to make, which is that snow climates are not a hard and fast rule. It's definitely worth remembering that avalanches are driven by weather, which can vary from day to day. And when you're describing a snow climate, what you're really describing is broad general trends in the weather. In fact, a snow climate in a single zone can vary between seasons. So, one season, a single zone could experience cold air temperatures and very little precip, which leads to a snowpack that is thin and layered and fairly unstable and generally continental. But then this same zone the next season could experience relatively warm air temperatures and heavy precip, which leads to a deep, well-rounded, generally stable maritime snow climate. Alaska is also pretty unique in that you can have two very different snow climates occurring over a small geographic region. So, a great example is the Turnagain Pass area, which tends to be snowy and warm and generally maritime, and 20 minutes down the highway in the Summit Lake zone, where it tends to be cooler with less snow and is generally intermountain. All right, well, that wraps it up for mountain weather and snow climates. Thanks for tuning in, guys.